Hey all, welcome back. This is 16.8 through 16.10. So we've got a lot of things to cover, so we're going to just jump right in. So first off, 16.8 talks about the acid-base properties of ions and salts. There are some salts that have pHs, even though they're not really acids or bases, and we're going to talk about those here. So let's start right in. Anions of weak bases. So remember, an anion is a negatively charged particle, so we need to remember that. So an anion is the conjugate base of a weak acid. An anion that is a conjugate base of a weak acid is itself a weak base, because remember, conjugate acid-base pairs kind of lends ourselves to that. But an anion that is the conjugate base of a strong acid is pH neutral, which means that it won't form a solution that's either acidic or basic, and that's because we're never going to be able to make a strong acid from its conjugate base. That doesn't make sense. If I throw Cl in solution, I'm not going to get hydrochloric acid. That just hopefully should make sense to us. So if we check this out, our first example, we've got NO3 minus. Well, that is the conjugate base of a strong acid, HNO3. So this one is going to be pH neutral. If we look at the next one, NO2 minus, that's actually a weak base. So that one, we said, is going to be a weak base. So this one will be a weak base. If we look at C2H3O2 minus, that's the acetate ion. Acetic acid, also a weak acid. So this one's going to be a weak base. Now, something that we can use from there is Ka times Kb equals Kw. So whatever our Ka or our Kb is, we can find Kw from it. We can use Kw to find Ka or Kb depending on what we have. The other item that we need to know is that pKa plus pKb equals 14. All right, and P is the negative log of whatever we have. So if it's Ka, we're taking the negative log of our Ka, and Pb, P K sub B, we're taking the negative log of it. Okay, so rolling on. This example right here says find the pH of a 0.1 molar NaCHO2 solution. The salt completely dissociates into Na pluses and CHO2 minuses, and the Na plus ion has no acid or base properties. So if we look at this, the first thing that we need to do is write our equation. And what we have is we have NaCHO2, and it breaks apart completely, so only a one-sided arrow into Nas and to CHO2 minuses. And so what we're officially interested in is not this and not this. We're actually interested in the CHO2 minus. So if we add that to water, which is essentially what's going to happen, we're going to get, we're going to get OH minuses, and we're going to get HCHO2 as another thing. So what we're going to be interested in is the OH minus concentration. And it said that we know that this dissociates completely. So we have 0.1 molar, water, no, 0, 0 here, minus X, plus X, plus X. We're just making our handy dandy ice chart. So at this point, we have an equilibrium. So let's go ahead and throw this over here. We're going to now have Kb because we're looking for OH minus. So if we write our equilibrium constant expression, we've got our OH minus times our concentration of HCHO2 over our CHO2 minus. So at this point, we would like to go and be able to look up our Kb, but they're not going to list a Kb, but we can definitely find a Ka. So what about the Ka of HCHO2? And that's equal to 1.8 times 10 to the negative 4th. So up here, we knew this. So what if I say 1.8 times 10 to the negative 4th times Kb, which is what we're looking for, is equal to 1 times 10 to the negative 14th. our Kb would hopefully come out to be 5.6 times 10 to the negative 11th, if we plug that into our calculator. So now we're ready to just plug this in and roll. 5.6 times 10 to the negative 11th equals x times x over 0.100 minus x. Again, we're still going to eliminate that minus x because it's going to be really small. So we've got x squared over 0.1 equals 5.6 times 10 to the negative 11th. And we're just going to jump ahead to what x equals. X is going to be our hydroxide ion concentration, but it's also going to equal 2.4 times 10 to the negative 6th. All right, at that point, we're now ready to plug it in. Honestly, I like to go POH equals the negative log of my hydroxide ion concentration, and then we can get to pH from there. So we've got negative log of 2.4 negative 6. That will be 5.6197. All right, and then we're going to add, or we're going to take 14 minus that, which should give us 8.380. 8.380 is what our pH should come up with if we're doing sig figs. All right, simple enough. So that's using Ka times Kb equals Kw, so that's kind of important. All right, let's keep rolling on. So that was anions of weak bases. So let's look at cations as weak acids. Cations that are counterions of strong bases are themselves pH neutral. So that's just kind of what we saw above. A cation that is the conjugate acid of a weak base is a weak acid. And small, highly charged metal cations such as Al and Fe form weakly acidic solutions. So let's look there. This one right here, C5H5NH+. Well, that is not a strong base. It's not one of our 8 strong bases, so that tells me it's going to be a weak acid. All right, if we look at the next one, calcium is the conjugate acid of a strong base, so this one is neutral. All right, we are not going to form calcium hydroxide. Not going to do it. Cr3+, this is probably one of our small, highly charged metal cations, such as Al. So we're going to say weak acid. All right. Kind of in summary, what we've got going, salts in which neither the cation nor the anion acts as an acid or a base form pH neutral solutions. We've got an example there, NaCl. Na is the cation of a strong base, and Cl is the anion of a weak acid. So this baby, these guys are both neutral. Salts in which the cation does not act as an acid and the anion acts as a base form basic solutions. So again, Na is the cation of a strong base, so pH neutral, but F is the conjugate base of a weak acid, so it will be slightly basic. All right, keep rolling. Salts in which the cation acts as an acid and the anion does not act as a base form acidic solutions. All right, salts in which the cation acts as an acid and the anion acts as a base form solution in which the pH depends on the relative strengths of the acid and the base. So at this point, this is where you have to compare Kas and Kbs to see which one is stronger. All right, so let's take a look. We've got SrCl2. SrCl2. Sr is the cation of a strong acid. Cl is the anion of a strong acid. The other one was a strong base, sorry. So this one is neutral. All right, AlBr3. This Br is the anion of a strong acid, and Al is one of those slightly large positive charges, so we said acidic. Sorry, tried to put an E on there. CH3NH3NO3 is going to be acidic. And that's because the NO3 is the anion of a strong acid, and CH3NH3 is the cation of a weak base. And then NHCHO2, we saw that one earlier. That one is going to be basic or a weak base, or basic in solution. And then the last one, NH4, NH4F. This is where we have to do a little bit of work, but what we're going to end up seeing is that the Ka is going to be larger than the Kb, which gives us an acidic solution. If you don't understand that, the book does a great job of going over it. Okay, on to